everyone, and welcome to this Neptune CFD droplet tutorial. This is a droplet-laden flow in a domain filled with both air and helium. A volumic inlet is set inside the domain, which injects droplets. So first of all, you need to create a steady called Droplet with a case. Then go in the Neptune CFD directory where the installation files are present and copy the mesh into your mesh directory. Then go in the data directory and launch the Neptune CFD command to launch the graphical user interface. When the interface is opened, you can go in the mesh and add the mesh you just copied, so mesh droplet.med. And for this case, we're going to execute mesh preprocessing only, so we can extract the different boundary regions automatically. So save your simulation and run the calculation. Once it's done, go on boundary zones and import the preprocessor.log created in the residue directory. You can see that the 3 boundary regions are imported automatically. So bottom, top, and wall. Then go back in the mesh tab and switch back the execution mode from mesh preprocessing only to standard computation. Then click on calculation features and choose Eulerian multiphase with the droplet laden flow. Then click yes. After that, go on main fields and change the different label for steam and water. Activate the energy resolution for both fields. In this case, both steam and water are compressible. Then click on turbulence models and choose a K epsilon for the steam field. And for the reverse coupling, choose small inclusions for water. Then on body forces, add the gravity on the Z component. Then click on non-condensable gases and add 2 fields. The first one is air. The air properties are automatically set. And the second one is helium. So you need to change the type from air to helium, HE. Then click on closure modeling. Click on the first interaction, steam, water, and set known for the lift. Then click on interfacial area. For the water field, set constant for the model with a default diameter of 1 mm. After that, click on volume conditions and check initialization so you can initialize fields. Then click on all cells. You can see here that the cathar tables are already taken into account. So you can click on the initialization tab. For the pressure, let 1 atmosphere. Then for the steam field, initially there's no velocity. For the fraction, set 1. For the thermal properties, set saturation enthalpy. For the non-condensable, for the air, set the following expression. If Z is lower than 0.5, set a volumic fraction of air of 0.8, else set a volumic fraction of 0.2. You can copy that expression and paste it for the helium field. The only change is if Z is greater than 0.5, and replace air with helium, He. For the water field, initially there's no water, so velocity of 0, volumic fraction of 0, and you can let the temperature. On boundary conditions, the three regions are walls, and no need to change anything. You can let the 0 flux. For the time settings, set an adaptive time step with a time analysis of 2 seconds. Then on post-processing, set an output every 5 time steps. On the writer tab, set an output every 0.2 seconds. Then we can add one probe into the monitoring points tab with the following coordinates. Click on Profile and add one profile called Alpha. With the following expression. X will vary from 0 to 1, Y is 0.5 and Z 0.2. You can set 50 for the number of points and just add the volumic fraction of water. Then click on Volume Solution Control and add on the post-processing the air and the helium, so you can see both fields in the post-processing. Then save your simulation, go in your source directory and add the inc user volumic inlet.c from the Neptune CFD installation directory. You can display the subroutine and see that the cylinder is centered in 0.5, 0.5 and has a height of 0.02 meter with a radius of 0.04 meter. The 1 stands for the secant phase, so the water for the droplets. Then go back in your data directory and launch the graphical user interface so you can launch the calculation. You can then open ParaView to post-process the results. We can display the water volume fraction to see the water droplets repartition. Or the air fraction, which is split by the water droplets.